Okay. So I had a question about some equation motion for simulated model. So continuation with simulated model. So yeah, so we have the action is equal to k 12 pi. So this is B and sigma, and then yeah. So this is action of what's with the model. So sigma is a 3-manifold R2. We already check. The B is a 3-manifold, which bounds the sigma. On the other hand, and then K is an integer, has to be integer. So that's we already checked. In particular, so this choice of B, so the action or partition function is dependent on choice of B. So we will check the choice of B and the extension of this G. So G is indeed the map from B goes to B algebra G, Lie group G. This we already checked. And the K has an integer. Yep. And then, so depending on the yeah, so depending on the partial, so the equation motion will give you this is question. So this is the equation motion. So this is equation motion, and then so here is you can see the anti-homological current has to be G inverse G up to some constant. I think K over 2. I put last time. K over 2 last time. Huh? I think it has. And then one student asked me the other. Yeah. So the last time I didn't. Yeah. Use my original plan is to derive this one as the in the homework, but I forgot to put it in there, so already passed too long, so it's okay. I'm not gonna put this in the homework. So sorry, this is a holomorphic current. So then the question is how to derive is the from here to and the question is how to derive this one. And in fact, so you can easily show that this is indeed equal to so G inverse and then G inverse. Can you show this one? So can you show this one? So let's see. So as we recall, so G inverse is equal to 1. Therefore, partial G inverse is equal to plus G and partial G inverse is equal to 0. Okay. Therefore, partial G inverse is equal to am I doing crossing? Okay, G inverse. Anyway, so let's do that. So that's we already showed last time. Minus sign. Okay. So therefore, if you plug, and also the anti-homomorphic derivative is the same. So therefore, if you do the following trick, so if you do the Leibniz rule, so you have G inverse, G and G inverse plus G right, and plug this one into there. We can have this is equal to minus G inverse sorry, G inverse do you agree? Do you agree? And the plus do you agree? So I just apply this guy into here, and you get this one. And then now G inverse partial G and partial and del bar G inverse is indeed this guy acts on this one. Okay. Do you understand? And with minus sign. So therefore, you can see explicitly this is equal to this guy. Do you understand? Okay. So this is equal to indeed partial G inverse plus okay, you understand? So this is equal to okay, so you got the original. So therefore, holomorphic current can be written like this. So this one I didn't derive last time, and one student asked me how to derive this one. Okay, that's a fair question. And then, so last time in the first half of the lecture, I think I written like this, I think G inverse like this, but this is not true. Okay, do you understand? So that's how you derive the holomorphic current. Okay, in the any question? Okay, so last time, and by using Volta-Gash identity, so this J takes the value of the algebra so that the J of Z can be written as a J of Z and TA, like this. And TA is the basis of Lie algebra. And then from Volta-Gash identity, we show that the TA of Z, GP of 0 is indeed the OPE is indeed equal to FABC, GC of 0 and Z square. Sorry, I think maybe I should. Okay, so this is A over 2 delta AE. Okay, so this is what we have derived. Okay, for other cases. So that's what we have derived. So this is the current algebra. And if you use the model expansion, what you get is the JAM, JPN is equal to so FABC, JC n plus n plus minus. I already forgot to quotient K over 2 n delta AB delta n plus n. So that's what you get. I miss I here. Of course, these Einstein conventions, the sum of C assumed, sum of C assumed. So this is called affine Lie algebra. Okay, so that's a symmetry. Another symmetry. In addition to the bilateral algebra, you have this current algebra, and we will see the consequence of this the affine Lie algebra or current algebra from now on. So that's why West-Zumino-Witten is very rich. Anyway, so I'm not familiar with condensed matter physics, but even condensed matter physics, there are lots of West-Zumino-Witten model up here. If you attend how to say colloquium, I forgot a few weeks ago by mention. He's a professor at Yale. He also talked about this kind of stuff, West-Zumino-Witten model. So. Yeah, I have no experience working in condensed matter physics, but still, West-Zumino-Witten model. I only work on the West-Zumino-Witten from the perspective, viewpoint from TQFT and also the string theory, but still, there are lots of application in physics. Yeah, of course, what I'm doing is not physics, not mathematics, mathematical physics. Of course, this guy's West-Zumino-Witten model plays a very important role, but even physics, it plays a very important role. Okay, so then, so this is the action of West-Zumino-Witten model, and what is the stress? Energy momentum tensor. And so we know, so most of you know already because you guys do the homework. And stress energy tensor should be K plus H hat. Sum of energy momentum tensor of a Wilson model, and H hat is called dual Coxeter number. And unfortunately, I don't remember the Coxeter number, but it's SUN, and at least I already know. Or in the case of SU, okay, the G is SUN, then H hat is equal to N. So therefore, you guys in the homework, you guys do the N is equal to 2 case, indeed. N equal to 2 case, N equal to 2 case, you have 1 over K. N equal to 1 over K plus 2, and then N equal to 2 case, and sum over A is equal to 1 plus 3. JA. That's what you have. So this is normal order, just usual normal order. So that's you already encounter on the homework. And so this coefficient indeed can be determined. So this coefficient can be determined by TTOP. So TTOP should obey desired form of the we will see. TTOPE should obey the like a usual form, right? TT C over 2 D over Z to the 4th plus T over Z to the square and so on. Okay, so that's what we need to and actually I mean last homework a bit unfair because I didn't a bit unfair because I didn't explain the lecture in the lecture about generalized OPE. So, but anyway, so when you said T of Z, so but you guys already actually this yellow book, I think he asked the question. So yellow book and section 6, and I think appendix B. So so they show that the generalized weak theorem, I think weak theorem or generalized OP or maybe OP. You have to use this one indeed. The OP is this current and J. And then stress energy tensor in Wilson-Witten model, you have to use indeed this generalized OP. So which I didn't explain in the lecture. So kind of it's unfair, kind of unfair. Actually, I didn't explain this one. So if you think you didn't get the right answer, you should take a look at this yellow book section 6 and then submit the homework again this week, because I didn't explain this one. So indeed, you have to use this general OP to get the right answer. And more precisely, so you have to use this JA of T dot is equal to sum over 2 pi I. And then I just take a so then U. So maybe I think we use JA JB and U. You will see. So you have to use this expression to get the right answer, and then the plot to of course JJ is just here is given here, and then maybe I should use B in that case B. And to compute TJOPE, you have to use JA0 and JA0. And then you should do the OP inside this integral by using this one, and then do the contour integral. Otherwise, you won't get the right answer. If you think you don't do the right thing in this last week in the homework, you can submit it again because I didn't explain this is section 6 point appendix B. So which is kind of unfair. So if you think you didn't do this problem, I think problem 2, right? Last week. You have to use this Jones-Wick theorem or whatever, Jones OPE to get the right answer. And also, yeah, whatever T with descendant, even whatever minimum model, some descendant operator minus n, O is a primary of field. So this operator, so this is descendant. If you try to compute this OPE with the descendant, you have to use this Jones-Wick theorem to get the right OPE. I think maybe I should include this one in the lecture notes. Sorry, I was too lazy to include this Jones-Wick theorem and the OPE. So that's why he asked like a month ago. So to get this right OPE, if you honestly do that. Okay.
Did you realize the O theory is applied to the non-primary field?
No, yeah, I mean this descendant also you can get the right OP. Anyway, so if you know, yeah, that's it. So this one I didn't explain. I briefly explained this one by WeChat, how to obtain the right OP. But anyway, so Ward-Takahashi, so using Ward-Takahashi in this state operator correspondence, you can also get this OPE by implicitly, not doing OPE, but by using Ward-Takahashi and also state operator correspondence, you can get also correct OPE. That's another way to get it. That's, I think, more lazier way to get the OPE. But if you really want to do the honest OPE, you have to use the Jones-Wick theorem. Anyway, so any good two? Some of you guys already applied this Jones-Wick theorem, and then I didn't, even though I didn't explain, but if you haven't if you haven't done it, you can submit it again. I would tell the TA to correct the, yeah. I mean, I wouldn't, how to say, withdraw the point 80% and so on. It's even though after the due date, I didn't explain Jones-Wick theorem, so it's okay. Then if you use this Jones-Wick theorem, we can just use TA of theta. Square, and so you can use it. So you can show this one. So therefore, J in so JA, the current of what's middle with the model JA of T is JA is primary. Birathoropian primary. Primary. Okay, so you can show. So if you look at this OPE of T and J, so you can show this with your third primary, and then again you can use. And then, if you compute TC by just plug that in and use this one again, Jones-Wick theorem, and so on, you can compute the TT OPE, and then what you get is C over 2, C to the fourth, and we have the desired, and then. That's we already encountered many times, and then C is equal to K dimension of the algebra K plus the arc set number. In particular, n equal to 2, 3, n equal, sorry, what am I doing? SU2, so you already show this is equal to, what is the dimension of SU2? 3, okay. So 3 coming from this 1, 2, 3. Okay. So 3k plus k plus 2. So that's you already shown. So this is the answer of central charge. Central charge. So this is the purpose of the homework last week, indeed, to derive this using general OPE and so on. Anyway, so okay, so therefore we have, in addition to, okay, so due to this, okay, of course, I think this is called Sugawara construction. Sugawara. It's a long time ago. I think he's in the director Sugawara. Maybe should I write in Chinese character? Sugawara. Construction. I can only write down the old character, but maybe simplified character will be different. Anyway, this is Sugawara construction. He is the he's now director of some institute in Okinawa. Okinawa is Junction, close to Taiwan. Anyway, so this is called Sugawara construction. And so in addition to the TTOP, we have a TJ and a JJ. So therefore, in with the model, the symmetry is much more much richer because of so minimum model and so on. Minimum model, of course, some minimum model can be. It's better not explanation. So minimum model for TTOP, now TJOP, TJ, I think I should TJOP and JJOP. So we have blah, 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 blah. So the symmetry is much more enhanced in Western middleweight model. In addition to bilateral algebra, you have a current algebra. Okay? Bilateral algebra, you have affinity algebra. So you need a combination. And if you do the contour integral, so you have, if you have this OPE, you just do the contour integral as usual to get the algebra. And you have the ordinary bilateral algebra, which is already you encounter many times. See the top, delta. Sorry, I think I should write down cube again. Delta n plus n cube. So this is this pronounced like Guanyin?
I think it's
Jenny. Okay. Anyway, there are lots of Sugawara, but he's one of them, most famous one, maybe. So this is a symmetry of the finally Western middleweight model. So in addition to bilateral algebra, you have another symmetry. So that's already written over there. FABC, GC, n plus k over 2, delta NP, delta n plus n. So these are symmetry of the Western middleweight model. And in particular, so we know T of C can be written as the whatever sum over Ln, Cn plus n, n plus 2, this way. well, I should mention. So from here, as you can easily see, this guy is the compound dimension of compound dimension 1. Compound dimension 1. So compound dimension up here, so it's a 1. And then due to this Gawara construction, so this can be Ln can be related to the 1 over k plus h. Check. A and m, Jn, n, Jn minus n, and then no mod. So this is L also can be written in terms of mod expansion. Yeah. Mod expansion. So this is the one way to derive this dimension of the higher space state in the homework. So as we know, so let's go back to the SU2 case.
In the second term, J for the subscript should be m minus n.
This one?
Here, in the last
This one?
No, the last, the Ln.
This one?
No. The last C node.
Let me check.
The fourth line.
This one.
I think it should be m minus n. N minus n.
I see.
Yes.
Thank you very much. Is it typo in my lecture note in that case? If you did a typo, I need to check. Oh, it's not check. It's not typo. It's my mistake. Okay, so that's the and then okay. So as I mentioned, so always, in fact, so Western with the model, of course, with it. So this is an important work by 84, and then Knizhnik. I forgot how to write the Knizhnik actually. Important work by Knizhnik is Zamochkov. Knizhnik. Zamochkov. Actually, personally, I met Zamochkov many times. He's Simon Center in the US. I personally met many times, and also with them. So these two guys constructed the Western Witten model. Unfortunately, Knizhnik actually died at a young age due to the heart attack. Yeah, he's from, of course, London Institute, and then he has a lot. I know many his friends already. Of course, at that time there is a so-called minimum, theoretical minimum Landau. So you have to read all the Landau's book, and then it takes a very super difficult exam, much more difficult than my homework. Anyway. So that's called the Landau school. It's notoriously difficult. He's a top student. He was a top student in Landau school. That's what I heard. But anyway, he died in very early age. I think I forgot, 85, 4, something like that. Right after he wrote this paper. Unfortunately, he was very well known genius, but anyway. So yeah, I think I heard in the subway he fell due to the hot attack in Moscow. That's what I heard from his friend. Anyway, So 84, but right after 84, but still, when general G, there are lots of mysteries. Even though this kind of symmetry you have, but there are lots of mysteries you have. Like already more than almost 40 years after the work. G is equal to SU2. G is equal to SU2, already many things are understood. But G's other group, there are lots of mysteries involved. So there are lots of open problems. And in particular, G's SU2, I already tell you so. I mean, JA is indeed, JA is equal to sigma A over 2. Can be understood as sigma A over 2. Sigma is, of course, power matrix. And you already learned in quantum mechanics, ABC, JC. So this is the algebra on angular momentum. And then we already know this representation. So if you have an algebra, you have to consider representation. So and then I already give you some example representation. Representation, for instance, so SU2. So if you look at the only SU2, so you have the J and M, 2J plus 1 representation that corresponds to the Young tableau 2J. So that's I already explained last time. And in this no, the due is next week, but this week's homework, you have to consider so-called continuous dynamical equation for G is equal to SU2. And representation always involve J corresponds to some Young tableau with single row. Okay. And then, of course, so since the affine algebra is an extension, so we already often like SU2 hat with level K or level K. So there's a so this is highest weight state. G of M for just usually algebra, and we know how it's a finite dimensional representation, how it works, right? So J plus, I already explained many times. So this is really basic. You have to understand the basic stuff to understand the difficult stuff. J plus and J minus, and so on. Raising and lowering operator, and go to up to J minus J. That's what you have for finite algebra. But for affine algebra, you have the more complicated stuff. More complicated stuff. I think I can erase this part. So affine algebra has weight state is H and J. And then H and J, of course, L0 acts on Hj as J plus 1 divided by K plus 2, H and J. Oh, sorry, I think I should mention that for when Jz, J3, 0 acts on Hjm, it's equal to, of course, Njm, and then J square. So L0 is essentially J square, as you can easily see. So Jm acts on, so that's you learn from quantum mechanics. So anyway, so when one students always come to my ask me to join my group, I always ask this kind of question. To understand they understand the quantum mechanics and so on. They understand representations of SU2, angular momentum algebra. So this is so-called Casimir. J square is of course Jx square, Jy square, and Jz square, You get this one. And of course, so this guy can be understood as the infinite dimensional generalization of J squared. And then the overall K plus 2 acts on K plus 2. And then L naught acts on just as a constant. And then you can have the many things. J naught 3 acts on J equal to J J. Okay, so that's the highest weight state. So this is, and then you can have the you start with Hj and acts the lowering operator. Lowering operator. So rating operator is to specify what is a lowering operator. It's better to specify what is a rating operator. N is greater than 0, and the A is any 1. Okay. And also J0 plus of Hj. So that's what we infinite. So this is finite dimensional version of SU2, the algebra, and this is the affine algebra with level K. Okay, and then we already know J runs for, since the algebra J runs for 0, 1/2, 1, and up to K, which means that the Young tableau has to be up to. So representation cannot extend up to K. Cannot like longer than K. So this is a particular phenomenon in the Western-Witt model. So in the finite dimensional real algebra, so J can take any integer, half integer, right? Half integer. On the other hand, affine algebra, you can take only up to K. So that's the main difference between finite dimensional and infinite dimensional algebra. I've been big slow, but anyway. I already always like go faster. Maybe it's better to go slow. Any questions so far? So one way to show this one. So this one is the using this one, using this mode expansion and then the mode expansion and then yeah, and then use a representation to get this formula, or otherwise you can also use the OPE to transform. That's you have already done in homework. Okay, so that's you already done in homework. Okay. And then we will see the consequence of the symmetry, so-called already not yet. Needs so much translation. Okay. So in minimal model, we already seen that the so there's. I already explained that the minimal model. Minimum model, you have the corresponding, the correlation function should satisfy so-called Zerabin-Porekov geometrical equation by inserting the so-called degenerate field. That's I already explained. And then with Zumino-Witten model, so-called you go K's equation. K KZ means quintuple geometrical equation. Actually, Zamochkov, there are two Zamochkov. They are brothers, indeed. They are brothers, and then I already forgot younger or older. One of them already has passed away, unfortunately. The other, yeah, the most famous one, actually, BPZ and then Z here, are in the Simon Center in New York now. And yeah, but if you try to study, I mean, I put some collection of the selected paper, collected papers of this compound field theory in the e-learning. If you try to learn the 2D CFT, this Zamochkov and Cardy's contribution is, I mean, to really groundbreaking, and then I kind of stuck in awe when I read their papers. So Zamochkov and Cardy are two big figures who construct 2D CFT. Anyway, so that's what we're going to learn. So minimum order, we have insert the degenerate field and find the differential equation correlation function satisfied. We can do the same trick in the Wilson-Witt model. And then, so we learn so the infinite dimensional Lie algebra and the representation. And so this is the highest wave state. So therefore, in CFT, you have a state of correspondence. State operator correspondence. So therefore, if you have a highest wave state, H and J, in G equals U2, there must be the corresponding primary field and corresponding primary field, okay, or corresponding operator. And we would like to see what kind of so the correlation function this operator satisfies. So to do that, so we just consider the last time. So we already see how the symmetry acts on the Wilson-Witt model, and then from here, 32. Yeah. So last time, so G, I already erased the action of the G. Wilson-Witt action G Z bar can be have a Fromov factorization. I think this is the Fromov factorization we have. And then we already noticed that the so under the transformation, so adjoint action Z of G goes to omega of G adjoint action. And then, so we know that this one is indeed equal to, so capital omega. So you just write down like this, infinite decimal transformation. So this field G is transformed and like this way. And also, so that's what we already done last time. And also, we have a water identity. Water identity is transformed under this in this adjoint action. Adjoint action 2 pi I. C omega A x and plus 1 2 pi I this is the water Gashanti for this adjoint action. And from here, one can just derive that the OBE with this field, or whatever, the JA of C and G WW is indeed minus TA. G, W, and W are Z minus W. So you just need to plug into him. G L Z G bar W bar indeed G W bar Z minus. So that's the OBE you get between the G that appear in the Western-Milwaukee action and then Western-Milwaukee current. Okay. So that you can just plug this one into here. So just instead of X, you just plug in G. G is the field that appear in the Western-Milwaukee action, and plug this one into here, you can obtain this one. Okay. Of course, so omega, I think it's omega A, P A, and so on. The Einstein convention is assumed. Sorry, I'm a bit slow today, maybe. But anyway, and so. So we can generate this OPE for the operator that corresponds to the highest weight state. So there is state operator correspondence. If you have a highest weight state, there must be a corresponding operator to the CFT or any CFT. If you have a state, you have a corresponding operator, and they behave the same way. That's the power of CFT. So we can generalize this. So if you have more generally, so given that, okay, let's fix on G. I mean, some of, maybe not so many people up here, and SUN. Let's consider SUN. So I already explained what SUN is. Then corresponding representation is something like a representation can be classified by Young tableau, this kind of Young tableau. And up to order representation. So often called lambda. It's called weight of representation. So SU2, you only have a single row. That corresponds to 2 times J. I already erased, I guess. Okay, here you say. So 2 times J, the number of boxes is 2 times J. Okay. But for SUN, the representation much more complicated. You have a much more complicated, more generated, so therefore more complicated representation you can have. So SU2, you have only spin J representation. That's you already familiar with. For SUN, you have much more complicated. And height has to be n minus 1. Height has to be n minus 1. And if you restrict the self G is equal to SUN, SUN hat level K, the width has to be also only K. So those are representation you can have. And if you change the Lie group or Lie algebra from SUN to whatever SON, SPN, or maybe more general Cartan type, the algebra, you have a much more complicated representation, and so on. This one is already, I mean, anyway, so some mathematician, I mean, it's already a long time ago, classified the cotton killing, but it appeared also physics. And since the representation much more complicated for higher rank, it's called rank. Higher rank. So even though you have a huge symmetry with the model, there are lots of open problems even to the CFT. For instance, like how to determine 6J sample for a Wilson model. That's a very difficult problem. Anyway, so given a representation, one can construct again the highest way state. And similarly, you can just generalize from finite to infinite dimensional, like for the G equals SU2 case. And you also have the corresponding highest way state. So therefore, given the highest way state, you can have the H lambda. H is of course the component dimension. I think yeah, so. Do I explain what is H? Yeah, this should be H. This should be H, right? No, not. Yeah. It's a component dimension. No, not H. And then of course this should correspond to the sum operator into the CFT. And in fact, you can just generalize this construction to have the OPE of the highest way state, and this is T lambda A, and then phi lambda of W, and so T A lambda is since it's a representation. Okay, I think. Okay, let's go slowly today in that case. Okay, so okay, let's talk about the representation of SU2. Maybe I'm not sure if I can reach to Jan Baxter. Some of you are expecting Jan Baxter today, but I'm not sure if I can reach Jan Baxter. Okay, so sigma x is equal to 1, 1. No, sorry. 1, 1, 0, 0. Sigma y is equal to I. Which one is minus sign? Forgotten. This one? Sigma z is equal to 1 minus 1, 0, 0. So this is indeed in the representation of the spin. So this acts on j is equal to 1 half. Okay? J is equal to 1 half. Okay? But when j equal to 1, dimension is 2j plus 1. So sigma x is mapped to 3 by 3 matrix. Sigma y is mapped to 3 by 3 matrix. Sigma z mapped to 3 by 3 matrix. In particular, so this should be I think I should put the 1 half, 1 half, 1 half, and this is 1 half, 1 half, 1 half, 1, 0, minus 1. So sigma z is always diagonal because of this property. And then I already forgot sigma j plus minus acts on jm is equal to jm plus minus 1 and some number, right? Some number. This is a Krebs-Gordon coefficient. I already forgot. So therefore, if you put the plus and the minus, of course, sigma plus is sigma x plus I sigma y, sigma x minus I sigma y. Then what you get is indeed 0, 0, 0, some number, Krebs-Gordon coefficient number, 0, 0, and 0, 0, 0, 0, 0, 0, some number, becomes 0. Do you understand what I mean? You don't understand. So here you have a j equal to 1, j equal to 1, m equal to 1, j equal to 1, m equal to 0, the basis of representation. Okay? And if sigma plus acts on J0, it becomes, so m equal to 0, it becomes m equal to 1, right? So therefore, if it acts on here, this middle guy hits on here, and it becomes upstairs, right? So it becomes m equal to 1. Okay? That is called representation. Okay? So even though, given us this matrix, so sigma x, sigma y, sigma z is indeed given a matrix. You have expressed matrix like this one because its representation j equal to 1/2. But if you go to j equal to 1, you have it becomes 3 by 3 matrix. But still, it satisfies this condition. It satisfies this algebra. Okay? The physicists like the basis, explicit formula. But however, mathematicians don't like basis. Mathematicians write down this algebra. Okay? Algebra. That's enough. We don't need this. We don't need this representation. It can be any matrix. Even it can be 3 by 3 matrix. It can be like a 100 times 100 matrix to satisfy this algebra. This matrix is called representation. Okay. You understand? So this number really appears. This number, Krebs-Gordon quotient. I already forgot. Square root j minus m, j plus m plus 1 or something minus 1 or something like that. This is Krebs-Gordon quotient. Anyway, so this number appears here. Okay, do you understand? And if sigma plus acts on m0, it increase the m by 1, like m minus 1, right? M minus 1 goes to m equal to 0. So therefore, this lowest guy, if you multiply this matrix, hits into here, and it becomes m equal to 0 after quotient. That's called representation. Do you understand? So therefore, so given the representation, so basis of Lie algebra becomes also acts on this guy by representation. Okay. So therefore, it becomes matrix, some matrix. So T A lambda is some kind of matrix, which is specified representation lambda. In the case of G equal to SU2, J equal to 1, it becomes 3 by 3 matrix. Okay. 3 by 3. And of course, the G equal to SU2 and J equal to J, it becomes 2J plus 1 times 2J plus 1 matrix. Okay. So that's it's called representation. Okay, I hope you understand what I meant by representation. And T lambda of A is really the matrix specified representation. Some of you already know about this fact. But anyway, so representation of the algebra is very important in physics, as you can easily see from here. And also J bar. I'm not going to write down the anti-homomorphic guy. Anti-homomorphic is the same, almost same. So therefore, this becomes the OPE that corresponds to the highest weight of representation lambda. And so therefore, what you learn in quantum mechanics is very important in any area of physics, even like anyway, even mathematics. I mean, in some sense, representation in algebra and the quantum mechanics is very closely connected. For instance, quantum group, which also appear from this St. Petersburg in Russia. One is Drinfeld, and another is a Kyoto group. It's a Kyoto group. Drinfeld and Jimbo, the Kyoto group, they also studied the actual integral system conformal field theory to find some quantum analog of the algebra, which is called quantum group, and so on. So there are also, I mean, the quantum group is already the subject of in mathematics, but it really comes from the studying of integral system also, a conformal field theory. So it's experimentation of the algebra and the quantum physics is very closely related. And yeah, I'm the one of the person who also work on this kind of connection, which is irrelevant in this lecture. But anyway, so from using this OPE, so this is called So this is called West-Newton. So given the highest wave state, you have an operator. So and this is called West-Newton primary. Now we call Witten primary. It's called Witten primary. Okay, so then so by analogy of the so here, so you can just have the model expansion of V as, so of course, as I mentioned, it's a JA has the conformal dimension of sum of Z n plus 1, JA n plus 1. So this is, JN. So this is a model expansion you can have. And then, so this is Witten primary acts on JA, acts on phi lambda as the minus t a lambda phi lambda. So this is usual action as a representation. Okay. So when G equal to SU2, lambda is equal to spin J, it becomes 2J plus 2J matrix. And then JNA acts on phi lambda is equal to 0 for n0. So that's what you obtain. So we don't need this, maybe. So therefore, and the L naught. So we know that the L naught. So L naught is Ln is equal to, I forgot, sum over m J A m J n minus m a Zn plus 2. So what I'm doing, k plus h hat. That's what we have for normal ordering, of course. So that's what we have. So therefore L naught acts on phi lambda is indeed equal to 1 over k plus h hat h check sum over a J0 lambda. Acts on phi of lambda. So therefore, and we know this acts on just matrix, just as a matrix. So therefore, 1 over sum over a ta lambda acts on phi. Okay, so that's the action of the L naught. So therefore, becomes conformal dimension. So this is conformal dimension. This becomes conformal dimension of this primary field, Western-Witten primary field, and the relation between if it is so therefore Western-Witten Novikov Witten primary means that the Virasoro primary do you understand what I mean? Western-Witten primary is the definition is given here. So JA axon phi lambda is this relation. Okay, this relation. This automatically satisfies T of Z of phi lambda of 0 is equal to H phi lambda of 0 Z square plus. So it's a good exercise. I already taught you by homework, so I'm not gonna ask you. But if you're honest person, you can just plug T is equal to Sugawara construction and use this OPE. You can just derive this equation. But on the other hand, Virasoro primary is not always the. This is not true. This is not true. This is not true. We already seen the example. So you have to distinguish Western-Witten primary and the Virasoro primary. Western-Witten primary is you have to satisfy this condition, but Virasoro primary you have to satisfy this condition, this kind of condition. TO is equal to H times the operator and over Z square and plus derivative operator over Z. But there's no higher order term. So we will see this example. For instance, the example which is Virasoro primary, but not the Western-Witten primary JA, the current algebra. So we know that the T of J, TC and JA are already erased, right? Unfortunately, I already erased stupidly. So this is equal to JA of 0 from C plus. So this is square. So this is already Virasoro primary. We already know. But when you set JA between JB of C and Z, we already know this one is equal to K over 2 delta AB Z square, right? Plus 1 over Z square should already show up, which does not satisfy this condition. Okay? So therefore, it's not Western-Witten primary. Do you understand what I mean? And then you have whatever I FABC, JC of 0, and then Z. Right? So this is the OP of JJOP. So therefore, JP is no longer Western-Witten primary. Okay. Do you understand? So therefore, Virasoro primary does not always mean the Western-Witten primary. Okay. Sorry, I'm a bit slow today, maybe. And then you can have the highest way state by lambda. Maybe here I should call phi lambda. And then you start acting on whatever J A minus something 1 or phi lambda to get the descendant with the descendant. Whatever J A minus N1 J A minus Nk phi lambda and so these are called Western-Witten descendant states. Should we take a rest? I can talk about K's equation, but it takes 10 more minutes. So let's take a break. And then I will talk about K's equation, and then briefly Cosette model, and briefly talk about Yang-Baxter. Okay. 10 minutes break. So how? So you could enter the campus freely without any restriction.
Yeah, just think about it.
Oh, okay. Somehow,
Daniel,
yeah, he mentioned he cannot enter.
yeah, he missed the third time COVID test
Ah,
yesterday.
I see. I see. I see. I see. Sorry, can I buy the one water for me? I cannot access. I will send you. I will send you by YouTube. Yeah, I send the money to you. Yeah. Oh my goodness. I forgot to print out a part of it on this equation. So maybe I should use iPad. So when is when is the exam date? December something? 30 or 29? I already forgot. Some students told me. Is this correct? Do you know? Can you check? So in addition to today's lecture, we have 3 more lecture. I think December 30 is the last. Huh? December 30th is the last day, right? So we have 3 more lecture. Okay. Then I can talk about Young Bucks for 3 more lecture. Okay. Okay, let's see how much I can explain about Young Bucks in that case. Yo. Yeah. Oh my goodness. Why my AirDrop doesn't work? Sorry, I forgot to print the Yanbox support and somehow I cannot transfer to my iPad. Just a moment. But I cannot move this camera. Does anybody have the USB to iPad? The connector? The adapter? I tried to use iDrop, but no AirDrop, but somehow my laptop doesn't see that. Why? Oh, come on. What am I doing?
You can use WeChat or something like.
Oh, I see. That's a good idea. That's a good
PDF?
idea. Yeah, PDF. That's a good idea. Okay, let me log in WeChat. Thank you. Where's the WeChat? I never. Yeah, thank you. And then log. Wait a moment. But if you log in here, I think I should do.
Now
Okay.
it can be
Oh,
online
okay.
in the same time.
Good. Oh, you can? Oh, good. Good idea. Let's file transfer first, and then log in. Unable to log in. Scan. Okay. Okay. Good. Thank you. Thank you. It works. What is this? Oh, good. Thank you. Wonderful. Now I can see that. Good. Shall we resume? Okay, so can you use geometrical equation? So the construction is really the same as BPC. BPC, and maybe I can erase here. So L minus 1, I think still here. The expression here is left L minus 1 acts on this with the primary lambda is indeed equal to 2 over k plus h check sum over j minus 1. J minus 1 and J0, J acts on phi lambda. So the rest of the mod, so there is always sum over m integer here, but if everything acts on annihilation operator, everything else acts on, because it's a normally ordering, so the annihilation operator goes to right and lowering, raising operator, creation operator goes to left. That's normal ordering. So most of the part it becomes annihilation operator, becomes 0. Okay. So, but only 0 part should not be, so m equals 0 part should survive. Okay. Sorry, I think I should. It's not. M equals 0 and m equal to minus 1. Okay. M equal to minus 1. So m equal to 0 becomes z0a, z minus 1a, and you have to swap the order because of normal ordering. And also m equal to 1, it becomes minus 1a, and then okay, this is m equal to 0, m equal to minus 1. Okay. So, and the 2 come from these 2 contributions. These 2 come from these 2 contributions. And we already know J0 acts on phi lambda is indeed becomes sum over A, J minus 1 A like this way. So seems like a minus sign here. So therefore, so this is now a representation. So that I just use this side. This side. So therefore, now if you act, it becomes new state. A minus 1 plus 2 A plus H hat sum over A, J minus A to lambda A by lambda. So it becomes new state. Okay? It becomes zero vector. It becomes 0. So, but you can just, I mean, here you can consider some operator, and you have some generator of this affine Lie algebra or Biot algebra acts on the operator. So you can consider also as some by using set operator correspondence, it can be understood as the new operator or singular operator. And what we want is essentially so we know that, and we know how L minus 1 acts on the operator. It just acts on derivative. So we know this by using for Takahashi identity, L minus 1 acts on just derivative with homomorphically. So that we already know. So we want to know how this J minus 1 acts on this phi lambda, and which is very easy because you can use this OPE. You can use this OPE. So indeed, so you can have a corresponding function, and then J minus 1 acts on phi sub I, acts on Zi, phi n, maybe Zn. So if you consider corresponding function, and of course everything is with Zumino-Witten primary. Then we can just using OPE. This can be written as EZ 2 pi I Z minus Zi. Maybe only this one. Then you can just have JA Z and phi. I mean, it's just an ordinary counter integral. It's very you already familiar with. So since you have a denominator Z minus Z only Zi, so therefore if you Zi what I'm doing Zi, and using this OPE, you should get you can extract the Z minus 1 A action on the phi I of Zi. That's you can just use the OPE with Jn and phi I, and you can obtain. You can extract J minus 1 part, and the rest of the part is a trivial. And from here, you can just obtain the this is equal to, so just use the OPE between JA and the phi and so on. So you can just obtain, just do the contour integral, performing residue integral. So you can just obtain this is equal to J is not equal to I, T, JA, Zi minus J. is the contour integral you can have. Here, so inside here, the contour integral is only around the, okay. So the complex plane, and you have Z1, Z2, Z3, and so on, and Zn, and you have a Zi. And here we assume the contour integral is only here. Like this way. But of course, this can be compensated by just doing the other part. The opposite way. Opposite way means the which way? The other. Same, right? It should be like this way, counterclockwise. Okay. Should be same. So if you do the blue integral, you get this one, and if you yellow or green integral, you get this. You get this. Okay. So this is the action of the j minus a acts on this one, and then plug that into here, and you get the famous. So if you consider we already know. So this. So you just insert. I mean, it's really the same as the construction of the with the BPZ equation. Of course, this is already new state. New states can annihilate the vacuum. New state can new operator can annihilate vacuum, and this can be understood as the partial Ci. So this is equal to 0. Ci plus 2 over k plus h hat h check plus. Like this way, acts on phi 1, C1, phi n. So this is the called conjugate geometry equation. K's equation. This is K's equation. So this differential operator acts on the Witten correlation function, primary. Correlation function with some primary is equal to 0. So this is K's equation. It's really the same as BP's equation in Miller model. So that's the K's equation, and G equal to SU2, and then phi I is correspond to some whatever the J equal to 1/2 representation. You can explicitly solve this correlation function, which is a homework of this week or next week. And then, yeah, anyway, so this homework is the last homework. I'm not gonna create homework for integral analysis on your Baxter. Anyway, so that's the K's equation. And this K's equation, anyway, plays a very important role in many places. Any questions so far? So this is the end of Witten. I mean, of course, Witten. If you try, I mean, I can spend 3 more lectures on Witten model. Okay, but anyway, this is at least the basics of the Witten model. And then there are lots of story going on, but I will ignore. If you're interested, you can just pick some book and then you can study more. Yeah, so also you can just there is a Lie group G and there is some sub-Lie group H. You can always consider some quotient space. So G over H, for instance, SU2, and U has a U1 subgroup, which is diagonal. For instance, we know SU2 is given by matrix alpha, alpha star, beta, and beta star minus, and then of course alpha beta squared is equal to 1. Okay? So therefore, it contains it as a subgroup as the alpha alpha star 0 0. So this is U1 subgroup where alpha is indeed equal to. So this is U1, right? This is U1 subgroup. Okay. So therefore, you can always take the quotient of SU2 divided by U1 and so on. Okay. So this is called symmetric space and or quotient space and so on. Corresponding to this one, you can construct so-called coset model. So this is called maybe coset model. This coset model is also plays a very important place in the conformal filtering. But I think in this lecture, it's no longer plays an important role in this lecture. But anyway, this coset model plays a very important role in many places. But maybe I can just skip this part and then move to the. Yeah, so one can construct from coset model to also 2D CFT. 2D CFT, some kind of variant of with zoom-in or width model. And if you, for instance, if you add some supersymmetry and so on, if you consider so-called super model, minimum model. For instance, I told you, right? So if you start with minimum model, you can have a T of Z and Z of Z. So they are the supersync partner for some cases in minimum model. P equal to 4, I forgot. So this is N equal to 1 bilateral model, and this can be related to SU2 cross SU2 divided by SU2. I think K plus 1 and 1. I already forgot the level. You can construct the coset model as the for minimum model. So it's equivalent. I mean, as a 2D CFT, they are equivalent. Super bilateral minimum model. And this kind of it's a bit more sophisticated stuff, but it also plays a role in condensed matter physics. For instance, SU2, K, and then U1K. This is called Fermion model. And this 2D CFT also plays a very important role in 2D condensed matter physics. But I'm going to skip because it's not going to appear in the subsequent lectures. In any case, so what we have learned in the very important model, so-called minimum model, and what's the minimum width model. So these are the so-called sits into the everything called a rational conformal filtering. So rational conformal filtering is at the so first of all, you have a unique first of all, it has so-called chiral algebra. It's called chiral algebra A. cross A bar. So we know that in the case of the with zooming with the model, A corresponds to the finally current algebra plus Birasol algebra, and then for even and also coset model, maybe coset. And a bar can be some algebra, infinite dimensional algebra, current algebra, Birasol algebra. So end up with this infinite is called chiral algebra. Chiral algebra, and it satisfies the following property: unique vacuum, and also finite many primary field. Primary field. And then so here space can be written, here we can decompose as some left-moving sector or homomorphic sector, and then on the homomorphic sector, and this has an multiplicity. And these are representation. So these are representation of A and a bar, and I and J is the finite many. Important thing is finite many. Important things finite many. I and J runs for finite many indices. But even though B itself is infinite many, so B, for instance, B is something like for instance, you start with whatever phi lambda, phi j, hj, and you act on whatever j minus 1a, h minus j, j minus 2a, hj, dot dot dot. So these are the representation, and of course sometimes you hit the null states and so on. You have to quotient the null state to get the reduced orientation. I think I should that you reduce. Let's go. You reduce representation. So those are bound module, and if you hit some null state, you have to throw away, and so on. So this will give rise to BG. And then you can have a tensor product, and you just bring a finite many copy, and you can have a Hilbert space. That's a typical feature of the rational compound field theory. And then all this minimal model with the model, coset model, all satisfy this problem. I forgot another property is the OP of primary field is closed among themselves. So this is property 1, 2, 3, 4. Okay. OP, so which means so you have a primary field O, A, Z, OP of 0, and then this can be written as O, C, and some coefficient ABC appear, and then some Z, HA plus HB minus HC and dot dot dot. So OA and OB is a primary field in the theory, and OC is a primary field in the theory. So since it's a only finite many field, primary field, so multiplication is just written as a sum of finite many C. So that's an important point. And in the homework, you use the Eisen model how to see this OPE of the Eisen model. So how many primary azimuth have in homomorphic sector? Do you remember? How many azimuth have? So, as I keep mentioning, azimuth fits into one of the most important minimum model. So there must be finite many primary field. How many primary field do you have in azimuth? Do you remember? Do you remember? So P equal to 3, M is equal to P equal to 3 is an azimuth corresponding. And I'll always write this kind of diagram 1, 2, 1, 2, 3. So these are primary field, and this is always identity operator in minimum model. I already forgot epsilon, so no, sigma. Is it correct? Is my file, is it correct? I already forgot. There's symmetry, right? Yeah. Let me check my lecture note. Sorry. Is it correct? So I made a mistake somehow. But anyway, so the spin operator and energy operator are the primary field. Yeah, I made a mistake. So sigma. So therefore, identity operator is vacuum, and spin operator, and also energy density operator. So the three primaries, indeed. Okay. So if you do the OPE, so of them, you have they're closed under the OPE. If you take the whatever sigma times epsilon is something can be written among these three. That's what I mean. Okay. Likewise, even with the model, there are finite many with Zumino-Witten primary field, and then you can just write down the Hilbert space as a sum of a finite many irreducible module in tensor product. So those are called rational coherent field theory, and the reason why it's called the rational coherent field theory is the central charge and all the coherent dimension primary operator is indeed, you can show the rational number. So if you look back all the H, for instance, H for SU2 level K with the model is H is equal to J plus 1, H K plus 2, right? So this is already a rational number. Okay. So with the primary is the compound dimension is the rational number. C is equal to you already derived, right? C is equal to 3k k plus 2. This is also rational number, right? K is integer. So with the model in the you can already check, and also if you look at the minimum model, you can always see the C and H bar H compound dimension is all rational number because they fit into the rational compound field. Okay. So that's a typical feature of the rational compound field theory. But if CFT has all anyway, I found anyway, so like a 2 or 3, already already forgot when I wrote this paper with my students. My first two students, we found a new conformal field theory, but some new conformal field theory always have a rational conformal dimension, and the central charge is the conformal dimension of central charge, but it doesn't fit into rational conformal field theory. We found some very weird conformal field theory by using considering some very strange by using so I already explained lambda gives CFT correspondence. If you consider some lambda gives correspondence CFT, and if you try to consider lambda gives model, some strange lambda gives model, you can find a new CFT, and which does not belong to our CFT, but all conformal dimension is rational number. Okay, I think that's enough with the model. Let's, I mean, in lecture note, there is a modular invariant partition function for with the model. I mean, if you're interested, you can read, but it's a bit too technical for students here, so I'm going to omit modular invariant partition function. And you guys pick the integrable system. I'm going to start talk about the integrable system from now. So we have 3 more lectures, so all are devoted for the so-called so I think there's a work by Beide in 30s. So nowadays go Beide ansatz. He introduced this Beide ansatz in 1930s, and there's an important work. Many people, Yan, the most famous Chinese physicist here in China. He's now Qinghua. He's almost like 100 years old, right? Anyway, Yan, maybe lots of people. Actually, no, Baxter, and many people sat on. Many people, not only Yan and Baxter sat on, and so on. From Yan's work is already 60, around 60. Their work is around 60s. They found some exactly solvable model in the 2-dimension, which I'm going to introduce from now on. Now let's go, Yang-Baxter equation. So from their work is the so-called integrable system. Sometimes in system, and also here exactly solvable model. Exactly solvable model. Scatter metric, as so-called sometimes as matrix, can be derived exactly. And then which contains so I'm going to explain so-called Beide ansatz equation. And also Beide ansatz equation, so-called Yang-Baxter equation. So I call it, this one is BAE. And here Yang-Baxter equation. So that's I'm going to explain in subsequent lecture. Probably today I'm going to talk about the very simple model of Beide ansatz, not the equation maybe. Some basic, Beide ansatz. So that particularly I'm talking about the 1930. We go back to 1930. And so as I mentioned, this Russian school in St. Petersburg actually really studied this integrable system, Faddeev. The school Faddeev studied this integrable system. And the mid-80s, they connect the integrable system CFT. But I'm not sure if I can connect to integrable system CFT. There are lots of connections in integral system CFT, but I'm not sure if I can reach within the 3 lecture. I kind of doubt it. I don't think I can go there. But anyway, so this is also very important exactly submodel. CFT is exactly submodel, which plays a very important role. And in particular, so this one plays an important role in Heisenberg chain. Heisenberg chain, spin chain. Maybe people call it the XXX spin chain. XXX spin chain. Anyway, Hamiltonian is just given by, so Hamiltonian is given by J minus J sigma x, and IJ plus sigma y. I mean, it's just a Eisen model. It's generalization Eisen model, and I and J. So this is the two-dimension Hamiltonian. I would say, yeah, one dimension and a time direction. 1 plus 1 dimension. This is called Heisenberg spin chain. One can apply this Benan's equation to the Heisenberg spin chain to get the exact S matrix. So that's what I'm going to explain from subsequent lecture. Unfortunately, I haven't written down the lecture note yet. Too busy. So, but fortunately, I will write down in the coming weeks. But anyway, so there's no homework and so on. So just be relaxed already. So then, and this part do not appear in the final exam. So just enjoy. Okay. So let's start. So what is the beta ansatz? Young's work is 67 indeed. Young's work is 67. He's a great physicist, but I kind of don't like. Anyway, it's better not to mention. It's recorded. I mean, I don't like the culture, like even East Asia, even Japan has like people worship worship great physicists, like they're already old people, but their work is already 60s. We have to produce as good workers as they do, but they even like in Japan, people just worship Yukawa or whatever number and so on, which I don't like, to be honest. Anyway, so yeah, of course they did a really great work, but it's worshipping is not good. This past work is not good attitude in physics. We have to produce as good work as they do. Yeah, it's like a religion for me. Yeah, I agree. It's I don't like this kind of culture. So what we need to do is just create as good, hopefully, as good work as they do. That's what we should aim for. Okay, so start to introduce beta ansatz is the simplest Hamiltonian is this one. You start with the 1 plus 1 dimension. So 1 plus space-time is the d is equal to 1 plus 1. So therefore, Hamilton formula is just 1 dimension. And then you just have the space one spatial dimension, and then you have any particle, any bosonic particle, And with potential delta function potential. So this is what really basic consider for this. The Hamiltonian is given by minus capital N like this. So this kind of Hamiltonian we will consider. So delta function. C is a coupling constant, some coupling constant. Say C is some coupling constant. So this kind of potential we will consider. And so as you know, it's like a billiard. So there's a time, and x. Okay. Xi really xi is the position of a particle, one particle. So you have, oh sorry, I think I and j are, and then so you have xi, for example x1, x2, the particle here, and as time move on, so it's just if there's no I mean, xi and x1 and x2 are different positions. There's no interaction. It's just free particle. So this is just a kinetic term in the Hamiltonian. It's just p squared, right? P squared. So it just goes straight. But it's like a billiard. So if you if particle goes to the same direction, there's a delta function potential up here. So therefore, it just somehow scattered in some way. Anyway, so like this way. So you just go like this way, by due to the delta function. That's what we are considering a system. Maybe I should write that like this way, maybe in that case. Okay, so this is a system better concept from in 1930s. Okay, since there is no interaction unless they hit each other, so this is really bad answer. So we just consider xi and xj. Xi and xj is the position of particle I and the position of particle j. And then we just consider the diagonal part. Always diagonal part is you have a delta function. You have, due to this delta function xi and xj, in diagonal part you have a delta function. So something special happens in diagonal part. And I call this part is region 1. Region xi is less than region 1 and region 2. So here something becomes discontinuous due to delta function. And what Ben consider, since this part and this part is there's no interaction, so everything described by this kinetic term, which means that you just have the plane wave. Okay? E to the solution of this energy is e to the ikx. Okay? That's what you learn in quantum mechanics. So what beta consider is phi 1 xi xj in region on this wave function. So you have to solve the Schrodinger equation, whatever. So h is over there, and then psi is a wave function. And the region 1 wave function, what beta consider is something like this. Aij of I e to the k I. So ki xi plus kj xj. Unfortunately, time is limiting. Anyway, so I'm not gonna rush because it's already the fun part. There's no so plane wave, and then psi 2. So this is called beta ansatz. Number 2 is equal to e to the by so this is what the so this is called beta ansatz. He assumed this is a solution of the this Schrodinger equation. Schrodinger equation. Solution of Schrodinger equation region 1, region 2 should be, so this is called beta ansatz. So I should call I xi, xj. So it's just the superposition or linear combination of the plane wave, and since there's a boson, so we assume that any bosonic particle, so system should be symmetric under the exchange of the two particles. Okay? Two particles. So therefore, so if you exchange the two particles, I and 2 are exchanged. So if you exchange x and j, the region 1 and the region 2 will exchange. Okay, but the system should be symmetric under this exchange. So therefore, this means that the bosonic symmetry tells you Aij of 1 is equal to Aj1 Aij or 2. So if you exchange xi and xj, the wave function should be the same. Xi and xj is exchanged, you get this one, this part, all right? So therefore, the coefficient has to be the same. And the same thing happens. Xi and xj exchanged, and you get this one. So I hope the longer one is j, and the shorter one is I. My handwriting is horrible, but anyway, you understand which one is I and j. Okay. So, and also from here, if you assume this one, so this means that the xi is equal to xj. So then you can have this psi I. It becomes coincide. Now, okay, I'm not gonna go into lush, but so now we try to solve this Schrodinger equation. Sure. To do the Schrodinger equation, maybe we can just introduce some coordinate. So center of mass. Okay, so first we want to solve the n bosonic particle, but locally we just look at locally two adjacent two particles. So let's restrict ourselves n equal to 2 case. N equal to 2 case. And then solve this Schrodinger equation. Now, of course, the Schrodinger equation, you can solve this one, but maybe it's better to introduce this point. So I and j, well, you can call it 1 or 2, whichever you call it. Just stick to the I and j are the two particles. And you can, so this is center of mass coordinate, and xi minus xj is the relative coordinate. It's called relative coordinate. So therefore, So Hamiltonian can be written to C delta R. Okay. So Hamiltonian can be just written like this. That's very obvious. Maybe there's a factor of 2 appear here or something. I'm not careful about factor. So you should do the computation by yourself. And of course, center of mass is always constant in 2 particles because there is no interaction term unless they hit each other. So therefore, so the wave function should be independent of the center of mass motion. So we just want to solve the Schrodinger equation psi plus 2c delta function of r psi. So and then we just this is Schrodinger equation. You have up to sine. I'm not careful with sine, to be honest. Okay, I think I should put the minus sign here. And then we want to understand what's going to happen around here. We want to understand what's going to happen here. And so here, of course, it becomes r equal to 0. R equal to 0. Relative quantity r equal to 0. And then we want to understand what's going to happen. So here, xi, xj are swapped between them. So therefore, the relative quotient is called a scattering matrix. Scattering matrix ij is called aij of anyway, 1 and 2 are already the same because of bosonic symmetry. J r. So this is scattering matrix. It's called scattering matrix. In other words, so this Ij and Aj is indeed the probability to have the I has a Ki momentum, J has a Kj momentum, is the probability Aij. Aj is the probability particle I has a Kj momentum, and then J has a Ki momentum, and so on. So that's the problem. And if you exchange them, so you have the scattering matrix. This is it's called scattering matrix. And then we just do the integration of this Schrodinger equation by dr between minus epsilon to epsilon. So r. So we are interested in this around here. R is indeed equal to here. It becomes minus epsilon to epsilon. So that's what we are interested in. So we try to extract the information of this delta function, because delta function only becomes effective when r equals to 0. And then, of course, this becomes, I will show, if you do the integral by parts of here, is psi about epsilon minus epsilon. And here you have a delta function is equal to, I think, I'm not careful about sign, so I may make a mistake. But you understand, if you understand the idea, you have to do the calculation by yourself. So, so that's how the irresponsible teacher gives some responsibility to students. Or to anyway, so this is the case, and then going back to another original comment, it becomes the it becomes the following. The following equation: pressure xi minus pressure xj acts on psi, then xi equal to xj plus epsilon minus, and then minus. Unfortunately, I only have 10 minutes left. xi minus is equal to xj minus epsilon is equal to c of psi is equal to xj. Okay, so this is the equation. You just bring back the relative coordinate r and just write down in terms of xi and xj. Then it becomes like this. Okay, so then plug this beta ansatz. So we know beta ansatz into here. And then solve the equation. What is the k? What is the k? Okay. Should I do that? I don't think I have time. Okay, maybe you guys just do by yourself. I'm gonna just plug this equation into here. So here, of course, it becomes xi is greater than, so this is psi I. And this becomes, oh, I already forgot to mention. Psi. And here, psi 2 becomes psi 2. You have to, because I mean, the region is the xi is less than xj. Okay? So you have to plug a psi 2 over there, psi 1 over there, and solve the equation. And then, so it's a bit tedious, actually. You have to spend 10 minutes or something. Yesterday I spent 10 minutes to derive this equation. But it's a simple exercise to do, and you can obtain. I'm not going to do that. I mean, if you're diligent enough, you can do the calculation. You can have a ratio between, of course, you have Aij and Aji. So you have you can obtain Aji and sorry, I made a why? Yeah, sorry, Aji, sorry, Aji, Aij. This you can have a scatter matrix if you solve this equation. So this is Sij, and this is equal to Ki minus Kj minus Ic divided by Ki minus Kj plus Ic. So you just plug the beta ansatz into here, you can obtain the scatter matrix. This is straightforward exercise to do. Even though it's a bit tedious, you just be careful of I and J and so on. And then just, I mean, this derivative, just pick the Ki, just Ki. And you have to be careful about the quotient, which one, Aji or Aij, and take a ratio, you get this. You can do it by yourself. Okay. Yep. And if the system periodic, if system is periodic, already erased. System periodic. Yeah, if system is periodic, so you can just have Aij and Aji. If system periodic, you cannot how to say it, distinguish I and J. So therefore, this has to be if the system is periodic, Sij has to be 1 because Aij and Ji cannot distinguish. From here, you can solve E is equal to Ki square plus Kj square. Exactly. So just plug in equal to 1 and solve this equation, and then you can solve this. So you can determine. Can be determined. By solving. Y is equal to Ki minus Kj C and Ki minus Kj plus IC. And then plug that into here, you can solve this system exactly. Now, so this is two particle system. Now we move on to the n particle system. N particle system. So n is general. So then, so we consider the wave function again. So in configuration like a, for the sake of generality, yeah, x.
Sorry,
Yeah.
the equation means C is equal to 0. And it is only, maybe it's -1.
Why is it 0? Is it 0?
Yeah, C is 0.
Because the ki and the kj. Oh, okay. So there are no solution of this. Is that what you mean?
I mean, if this is equal to 1, then C
C
equal to 0.
has to be 0. Okay. Ah, okay.
Which means there's no interaction.
There is no interaction. Okay. I see. Yeah, you're right. You're right. Maybe I got something wrong. Two particle states. Okay. I think it's a. Okay, is she -1? I don't remember. Okay. Next time I will correct this one. Sorry. Anyway, so this is the scattering amplitude. You can have periodic. Forget about it. Q1, x, Q2, x, Qn. So you just consider the following region. The L. So L is the length of system. So you just consider the one dimension. We have x1, x2, x3, or xq1, xq2, xq3, xqn, and you have a L, 0 to L. So you just consider the following region, and in this region, you just assume the beta index. So this is the wave function takes the following form: P, A, P, and Q, exponential sum of it's the same generation over there. K, Pi, and Q, XQI. I runs for 1 to n, and P is some symmetric group. And factorial. Symmetric group, you know, right? So 1, 2, 3, 4, whatever, and you can just swap number 2, 1, 3, 4, n. This is one symmetric, and you can swap and so on. This is exactly the generalization of this two particle system. And A is the amplitude that have this. Okay. So again, so here, so it's just a linear combination of plane wave, but you have to shuffle of the indices. So this is beta index. So again, so you have that function, but so now similarly we can define the scatter metric Sij as the ratio between A and then the same thing, everything same, but Kj and Ki, and then Q So P instead of, I mean, P means KPI. So, and the ratio between the amplitude K I and the KJ. So this is scattering amplitude we're interested in. Okay. And now we just do the following, the trick. So if you assume this one, so you have a time direction, and then you have a L. So you have a L here, and you have a particle, whatever, XQi1, XQ2, XQ2, and XQn. And so we bring one of the particle, J, let's call J particle, to goes to the psi. So okay, so let's assume periodic boundary condition. I think that will tell us what I should do in this case. Xn. So this is periodic boundary condition, and now so we assume so the xj goes to. So we consider xj goes to xj plus f. Okay. So which means that the particle, whatever, so you have a xj somehow is go to somehow like this way and then come back here. That's what I'm going to do. So xj goes to L and it's periodic. So it's periodic. This part is time direction. Time direction L, and then so momentum K, and come back here, and so now so you have an interaction like this way. Therefore, so what you have is that so from periodic boundary conditions, so you have from here at each point you have a S matrix. S matrix. Sorry, I'm sorry, I don't have a time to. So therefore, e to the so the translation e to the kj L can be written as j I is not equal to j Sij, and which is equal to I is not equal to j Qi minus kj plus IC divided by kj minus ki minus IC. I think I made a sign wrong. I think the sign wrong. Like this. Sign wrong. So you can get this equation. And this is some kind of, it's called, so it's some kind of Beta-Analysis equation. It's called Beta-Analysis equation. If you solve this one, you can solve this one exactly, and find the spectrum of the E. So unfortunately, I don't have a time to talk about, and also I made some silly mistake over there. So that I will fix next time. But next time I will try to solve this equation exactly. So this is called Beta-Analysis equation, and from here you can determine energy spectrum. That's what I'm going to explain next time, and then after that I will go to talk about the Heisenberg spin chain. Okay, sorry. Yep. So this is just beginning. So yeah. So you have a scatter matrix, and you can solve this equation exactly. I will talk about next time. Okay.